I picture you and like your co-pilot, like in that scene in Caddyshack, just you're getting pelted by 3-inch hail, and you're like, well, I don't think the heavy stuff's going to come down for quite some time now.
Yeah, it was pretty loud. In fact, they put a microphone right on the front of the canopy. We recorded 2 channels of audio, the pilot's comments, and then this other hail mic, and the scientists could actually kind of gauge the size of the hail just from the loudness from that microphone.
Welcome back. I'm Dan Blewett.
I'm Alan Hall.
And I'm Rosemary Barnes.
And this is the Uptime Podcast, bringing you the latest in wind energy tech, news, and policy. All right, welcome back to the Uptime Wind Energy Podcast. I'm your co-host, Dan Blewett. On today's episode, we've got a great guest here today, a lightning expert, Tom Warner. So Tom has a really interesting background, which we'll get into. He was also a pilot in the Air Force and flew this legendary aircraft that we'll get into a little bit called the T28 Storm Penetrating Aircraft. And what this really means is that he was someone taking aircraft up into storms with the intention of seeing how they did, getting struck by lightning, getting hit by 6-inch hail, all this crazy stuff in the name of learning more about storms and lightning and how they all interact with planes. And also he's done a lot of research and photography, high-speed video on wind turbines. So a lot of stuff that you'll see in high-speed video, you can see how lightning propagates, the leaders, lots of stuff that has never been seen before. So Alan, give me a little more context into Tom, because to say like you're a lightning expert, but Tom is like the lightning expert for lightning experts.
Yeah, he's a resource for a lot of people because he's published so much and he's been involved in lightning reaching up from towers. And there's a whole series of papers and research. If you go to his website, you can download some of them or find out where you can get them. That it was research oriented on wind turbines and also tall towers that were propagating leaders up into the sky and creating these thunderstorm lightning events. And also, I think it's one of the early places that I saw where a lightning strike far downfield can trigger reactions in the cloud and create this situation where tall towers / wind turbines can start reaching out to the sky simultaneously. And we've seen a lot more images like that in the last couple of years, some of them from Tom, some from other researchers in the US and Spain and around the world. But that knowledge of weird things are happening in the cloud, and it has an impact on the way lightning approaches wind turbines and tall towers and the way lightning may attach, the polarities, just the different situations that may occur, that I think in Tom's neck of the woods, which is in South Dakota, a lot of lightning strikes on these tall towers are actually initiated by the tower or the wind turbine. And that changes the way we think about it, because I think like airplanes, we used to think lightning just happened and we were in the wrong place at the wrong time. Well, I think it collectively is changing now, where we think that a lot of the lightning events are actually triggered by the turbines or towers because they're so tall and they're in the wrong place at the wrong time. So our thinking has evolved, and a lot of that has come from Tom. I frequently his website, and he has a really cool YouTube channel that has great information. If you watch those things, you can learn a lot because they're in high-speed video. You can learn a lot about what's actually happening on a wind turbine or a tower in a lightning event. It's fascinating, really fascinating.
Yeah, it's interesting, the idea that these tall objects and planes and space shuttles that they're causing lightning. Because you think, like you said, you think of it as you're walking through Miami and a coconut falls off a tree and hits you on the head, and that's the end of you. That's very bad luck, kind of like getting hit by lightning. Right. But it's not really like that. It's more like you're going up and shaking a palm tree, right. And so then the coconut falls out. That's kind of like what these tall towers are doing.
Yeah.
Because they're there, they're triggering more lightning, which is a really, again, one of the many misconceptions that Tom will dispel in this podcast. So, it was a wide-ranging topic, and for all of you listening, it's you should stick around to the end because we get to the wind turbine specific implications for this towards the end of the show. He also gives a good foundation for what's happening in lightning. So if you need another dive into how it works and some of the way you learned it in school 20, 30 years ago might not apply today. So he's going to kind of break some of that down, which admittedly can be tough. So we're going to overlay a couple of video slides over on YouTube. So just kind of explain some of these concepts. But yeah, Alan, I mean, there's still a lot to learn with lightning, but seeing some of this high-speed, super slow motion video that he has from his various cameras set up around the world, he's been able to see stuff that was too fast for the human eye for all of human history until just recently with these new cameras, and that's really changed his view of lightning and again just broken down some myths that no, we know this stuff is happening that we assumed was not happening before.
That's right. And I think that sort of the big one here is the way lightning starts. We don't really understand what triggers lightning, what starts the whole process from happening. There's been a lot of discussion about cosmic rays, which may partially be true. But I think we're evolving into thinking like the air is just breaking down bidirectionally. It's nothing that goes triggered on one side and then it goes to another side. What's happening is we're breaking down the air and we're creating these leaders in the air without anything else happening. It's just a strong electric field, and off it goes. That's a different way of thinking about why lightning starts. And because we have so many cameras around the world, and everybody's photographing, and now the high-speed cameras are much more available than they were even 10 years ago. We're getting more and more data, and Tom was sort of the initiator of some of that, particularly putting it online so we could see it. And without engineers need to see it before we believe it. We can read it in a book, but we really want to put our hands on it and see data. Tom was our data source, and still is for that matter. So it really helps us, particularly wind turbines, helps us understand what is happening to some of these wind turbine lightning strikes.
Yeah, and Tom's, again, that big journey to gather all this data for the good of all of us started up in the skies in a T28 storm penetrating aircraft.
Yeah. And it was a 1949 T28 Trojan, which was a propeller, a big old radial engine trainer used for both the Air Force and the Navy. And back in the 70s, the Soviets were claiming that they could modify the weather. So there was an effort on the U.S. to try to create a platform that could fly through storms and clouds and measure in situ the microphysical things that are going on, and to verify if it was possible to modify the weather. So in the 70s, Paul McCready came up with a design for modifying an aircraft that could survive a severe plains thunderstorm environment. And so they put armor plating on it. They put 3/4-inch Lexan bulletproof canopy modifications with metal reinforcement. And then they hung all these instruments on the bottom of it so they could measure hydrometeors, which are particles, either water or ice, from the millimeter size up to 6-inch diameter hail. And so this plane was one of a kind. It's not a hurricane hunter, because the hurricane hunters, they go over hurricanes and they have 4 engines, but they don't get into the really heavy hail that we get into the severe plains thunderstorms. So this thing was unique. It was modified heavily. It could. We also had a sniffer tube, so we could measure oxides of nitrogen. It had electric field sensors, so we could measure the electric field and all the thermodynamic parameters that you'd want to be able to measure. And so we flew through thunderstorms and got into hail that made quite a racket. And we would get struck by lightning typically once a season. As a single pilot, they took the back seat out and put the chemical sniffer in the back seat. So it was just, you're there by yourself. You do talk to a ground controller that's looking at the radar, can see your position, and is getting some telemeter data so they can tell if you're in hail or the environment that you're in, but they also keep you safe. They tell you where to go if there's a problem. And so it was to me, a dream job as a pilot. An atmospheric scientist, a lover of severe weather. When the chief pilot asked if I wanted to fly it, I said, absolutely. And I was the only person that applied. And there's actually 2 people that applied. And when the chief pilot called the other person and told him what he'd be doing, he withdrew his application. So that was it. But yeah, we get struck by lightning. The one most memorable lightning strike, it attached to the propeller and the tail, and there's always two attachment points because it actually initiates from the aircraft and propagates bidirectionally and bipolarly. And the lightning channel, one of the attachment points was on the propeller, and the sniffer tube that was measuring the oxides of nitrogen was on the top of the canopy, and it went right over the sniffer tube and got a great data set and ended up in a publication. But when we land, we inspect the aircraft, and there's little burn marks and weld marks that took a little of the metal away from the propeller and the tail, and we'd file it out and they'd be ready to fly again. So
I picture you and like your co-pilot, like in that scene in Caddyshack, just you're getting pelted by 3-inch hail, and you're like, well, I don't think the heavy stuff's going to come down for quite some time now.
Yeah, it was pretty loud. In fact, they put a microphone right on the front of the canopy. We recorded 2 channels of audio, the pilot's comments, and then this other hail mic, and the scientists could actually kind of gauge the size of the hail just from the loudness from that microphone.
Well, before we get too deep, I kind of want to get you to go over just the basics, what lightning is, what lightning isn't, because I know a lot of what's taught still is kind of outdated and from old textbooks. So can you kind of give us a primer about all this stuff? You already alluded to a bunch of it, how you could feel, like the charge building up, and can you kind of take us through just the basics?
Sure. I mean, I think that the most fundamental thing you have to think about is how does the whole process start? And it starts with the electrification of a storm. And the way a storm electrifies is that you have ice particles, what we call graupel, which is small hail, soft hail, and then you have ice crystals. And these particles can collide. And when they do, in the presence of supercooled liquid water, so we have to be in a temperature where it's below freezing, there's these droplets of water that are not frozen, even though it's colder than freezing. And that creates a rhyming scenario to where if any of those water droplets touch an ice particle, they'll freeze instantly and create rime ice. So there's a process that takes place that when these ice crystals collide with a piece of graupel, electrons are transferred to the graupel, and the graupel takes on a negative charge. The lighter, smaller ice particle tends then to take on a positive charge due to the deficit of electrons. And in the updraft, then that separates it because it's a lighter ice particle. So the ice particles collect in the upper part of the storm. The negatively charged graupel collects in the lower part of the storm because of the larger size. And so a typical arrangement of charge in a thunderstorm is an upper positive charge region and a lower negative charge region. And then for what we see over time is that another lower positive charge region forms, and this is due to induction and a few other processes. So it's really a tripole type structure is your typical. Now, it's much more complex than that, but that's the basic.
This ice is present no matter the ambient temperature, the time of year. I mean, we're talking about pretty high up in the sky, right?
Right. It's going to vary depending on the time of year. Obviously, in the summertime, we're looking at higher altitudes because of the warmer temperatures, and that's why we flew around 20,000 feet in the thunderstorm in the storm plane, because we were wanting that minus 10 degrees Celsius, and that was around 19 to 20,000 feet. And the winter months, that's much lower. You can even get freezing down to the surface. But you don't get that instability, and you typically don't get thunderstorms in the wintertime because of the cooler temperatures. So now we have this electrified storm. So what is lightning? Well, lightning is the development of a charged plasma channel. Essentially, it's a hot, visually bright plasma channel where the neutral air of oxygen and nitrogen breaks down. And when we say break down, what that means is it ionizes. So the air molecules have an electron rip off, and then you're left with a positive ion. And the reason that happens is that you have these charge regions, and there's an electric field between those two charge regions. And it gets so strong that you can get ionization of molecules, the neutral air, and that causes separation. So you can think of it almost like a metal rod in the sense that it's conductive. It's got a plasma charge, can move. It's very conductive, and it develops in a bidirectional bipolar fashion. And so think of it as just the air is breaking down under the intense force of the electric field. The actual mechanism that starts that initial breakdown is still being researched. It's not fully understood. We don't know if it's a cosmic ray that comes in and knocks off that first electron, and then now that electron on the force of the electric field accelerates and causes an avalanche of collisions and other ionization. Or we don't know if it's an enhancement of all these hydrometeors that enhance the field locally that create the condition for the initial ionization. But we're getting closer. But it's one of those fundamental questions that are still not fully understood. So lightning is simply the development of a leader, of a plasma leader that's conductive, it's hot, and it grows in a bidirectional bipolar region. So you have to have two charge regions for this to grow in between. So that's how a lightning flash. And it's only leaders. Leaders can propagate, and they'll continue to propagate based on the difference in the potential or the charge on the tip of the leader and the charge region that's in the storm. So if you think of the negative end of a lightning leader, it's got a surplus of electrons. So it's attracted towards the positive charge region. We have negative and positive, so it's attracted to each other. And the negative end of the leader, which has a surplus of electrons, goes towards the positive end. The positive end of the leader, which has a deficit of electrons, goes towards the negative charge region that has a surplus of electrons. And so it's this difference in charge that drives the leader. And it causes further ionization on the tips, and that's how it grows. So it's ionization on the tips of the leaders that cause it to grow. As long as there's a difference in the charge between the tip of the leader and the cloud charge, it'll propagate. Once that difference decays, the leader just stops, and then it cools down, the light goes away, and those ions and electrons start recombining, and you're left with the neutral. But overall, what you've done, if you have these two charge regions and you have a lightning flash in between it, it shifts charge towards one direction. So in other words, the positive charge region, you'll get a shift of electrons, and in essence, you've reduced the charge because of that shift. And that's what's going on. So unfortunately, for many years, it was taught that, this charge in a cloud is like a water balloon, and it can flow, and you poke a hole in it, and negative charge comes to the ground and strikes the ground. And that's not true. It can't move like that. It's on these little ice particles, and it can't flow on its own. And you hear the analogy of a doorknob. Well, there's the charge in a cloud is not a doorknob. It would be really bad if it was, because planes wouldn't be able to fly through and they'd hit it. But all these little ice particles are like doorknobs, and they got charge on it, and they can flow if they touch something, but they can't move rapidly on their own. So that's a myth or a description that's outdated. In the case of lightning, it stays in the cloud and it moves bidirectionally and stops. That's a cloud flash. But you could have one end of the leader come to the ground, and there's charge induced on the ground. The Earth is a fairly good capacitor or conductor in the sense that it can allow charge to move very freely along the surface. So if you have a negative end of a leader go outside the cloud and start coming towards the ground, there's going to be positive charge induced on the ground. And so it's going to be attracted to the ground. So that one end of the leader can go and make a connection with the ground. And when that happens, it causes what we refer to as a return stroke. Because suddenly you have this charged leader that's under a certain level of resistance, touch a conductor that has very low resistance, and the electrons rapidly accelerate downward. And that causes increased kinetic energy, thermalization, and you get this bright, hot return stroke that cascades back up the channel in kind of a wave front due to the sudden increase or decrease in resistance. And that's the return stroke. And that's what we see as a really bright event that strikes the ground. But we can still see the leaders as they propagate through the cloud, because we see cloud flashes. We see the leaders. So we're always seeing lightning. Whether it touches the ground or not, we can see it.
And so what's the difference between upward and downward lightning? Because that's definitely a cause for confusion. Because you think they can only go one way. Like as a kid, you learn that they go down, but then you're like, wait, then people confuse you and they tell you they actually come up. You're like, well, which is it? I just want to look at lightning. Like, I don't know.
Yeah. I was taught as a kid and most people I come across is like, well, I was taught, lightning always goes up. And it's true that the return stroke that I referred to goes up. It goes from the ground up because of that resistance decrease. But lightning, like I said earlier, is a bidirectional bipolar process, and it can move. It initiates up in the cloud, except for upward lightning, which we'll talk about later. It propagates bidirectionally and actually comes down to the ground to create a cloud-to-ground lightning flash. So it actually moves downward. It actually moves in both directions, both upward and downward, because there's part of it that you got to think of lightning in terms of both its ends. We're just seeing the lower end come below the cloud and come to the ground. There's an upper portion that's growing upward into the positive charge region. The negative end will go up in the positive charge region, and then you could have the positive end come down, and vice versa, depending on the charge arrangement. So there's always two ends of a lightning. And then when it touches the ground, after it attaches the ground, causes the return stroke, it can continue to grow as an attached channel further up into the storm. And that's what we see is happen. And that's essentially what upward lightning is like. So the process is straightforward in that regard, but really lightning comes down from the ground, causes a return stroke, which goes back up the channel. And that's where we were taught lightning always goes up, because they were referring only to the return stroke, but that's not really true. It actually comes down.
And the most of the things we know about lightning have happened in the last 30 years, I would say. We knew that we could see lightning flashes, and we photographed lightning flashes back in the 1920s and 30s, and had a sense of what some of the basic physics were, I think, just because of what we could record. But in the last several years, that's really changed a lot, because now I think our model has changed from sort of the doorknob model or the water balloon model to more of a global model of there's charge entering the upper atmosphere out into space, and then there's a lightning flash down to Earth, and then the lightning can, because it's like a series of dominoes in these huge, massive charge centers in these clouds, you can get cascading things happening in the sky. And I think that's one of the more interesting pieces. We've stopped thinking about lightning as single events. We're looking at more like almost like a living, breathing organism. It's changed in its nature. And you're right. We still don't really know what starts it, but I think we do know more about the intricacies of how it travels, how it migrates, how the charge centers play into that. And one of the questions I always have is how, when we start thinking about lightning globally, and we're trying to evolve that into, I have a house, or I have a tall building, or I have an airplane, or I have a wind turbine, and how lightning starts makes a big difference onto what and how it develops in the cloud actually affects what happens to this device we've created and want to protect. Walk us through a little bit of things that, because you do high-speed photography, and I want to understand the high-speed photography aspect of this. So let's go first through that one. In the high-speed photography, you started doing high-speed photography before people started doing high-speed photography. and at the same time, you're putting it up on the internet. And us engineers grinding away, trying to learn about lightning and at the time design airplanes and wind turbines, we're just absorbing all this stuff because it's so fascinating. We've never seen this before in this sort of resolution. What drove you to get to do that? Well, what was the impetus to say, hey, we need to be recording lightning? Well, I'll just take a camera out here and do it.
It really started back in 2004 when I witnessed a spectacular upward flash. I had retired from the Air Force. They retired the storm plane, so I wasn't flying the storm plane anymore, but I was still very interested in severe weather and lightning in particular. And so I had a number of cameras, digital still cameras and standard video cameras that were always pointing towards storms in Rapid City. Had a nice vantage point. And so I witnessed a spectacular upward flash in 2004 from the tower, one of the towers we have in Rapid City. We have 10 towers and communication towers on a ridgeline that run through Rapid City because it's kind of the hub for the region. And I saw this thing and it was just blown away, and I wanted to understand it better. And I had the fortunate experience to work with a number of lightning scientists when I flew the T28. It was always a collaborative effort with all our research projects where we were working with lightning scientists and radar science, the radar meteorology, all aspects of weather. So we really got to know each other. And so I reached out to them and I talked to them about it, and they helped guide me and mentor me into my research of lightning, specifically upward lightning. And really at that time frame in 2004, there were scientists that were using higher speed cameras up to 1,000 images per second. Dr. Vlad Mazur used them in the late 90s. And then Marcelo Saba, Dr. Marcelo Saba in Brazil was using one that was 5,000 images per second. But it really wasn't known or shared much, and the analysis and the production of papers were still in the works. And as a photographer, I have a very strong photography hobby in addition to my flying and my severe weather interest. After seeing that, I just wanted to experience it in a better way. And it's like, this would be so neat to be able to slow it down. And how do I do that? So it took me about 3 years of research, doing it with the standard speed cameras, that I started learning more about the high speed cameras, the Phantom Vision Research Phantom cameras. And then in 2007, I had heard that Tim Samaras was filming with high speed cameras, and he also got this camera, the Big Kahuna, that was used for nuclear explosion photography. So he was an amazing engineer. Yeah. And I had a chance to just talk with him, and I said, I know you're getting into this high-speed lightning videography. This is what I'm thinking. Do you think that'll work? And he said, yeah, that should work. And so we talked a little bit, and that's when I got my first camera. So the difference was that, I was more of an independent. I was able to purchase the cameras and do the cameras without restrictions from federal funding or anything like that. So I made that stuff available. Sure. and much easier to access, which was my intent all along, is that I want to share what I learn and make it available, because I think it's important to learn and be educated about the world around us. And so I think that's why, my stuff became more and more prevalent, was because I made it more easily available, because there are a lot of restrictions too when you do federally funded projects on what you can do with the data and such that you acquire and the equipment that's purchased through those funds. So, but that, after that, I think the photography aspect, my background in photography, really helped a lot, because I had a perspective of creativity, understanding of the photography. And that really helped accelerate the use of high-speed cameras. We talked a lot amongst the scientists, the lightning scientists, on how best to apply these. And Marcelo Saban and I really worked hard to do it in the best way possible to get the best data. And so we were kind of the focus on development of those techniques.
And so that's, you talk about leaders, and they're maybe not quite as fast as the lightning stroke, and correct me up, I might be wrong there, but they're very small and they're harder to see, right? But they sort of trickle along down the sky, almost like a dashed line on a map.
That's exactly it. The speed of the leaders are typically 10 to the 5th meters per second. And as a scientist, you're always thinking in those terms. So that's why I said, so you're looking at 10 to the 5th meters per second on that scale. Now, the return stroke is 2 orders of magnitude faster. The return stroke's 1/3 of the speed of light. And so when that wave of increased acceleration that goes up the lightning channel is incredibly fast. And so 2 orders of magnitude faster. And we've actually measured differences in the negative and the positive ends of the leader. And that is one thing that I find most fascinating, is the behavior differences between the negative end and the positive end. the physics are different in that how the air breaks down, how the electrons are liberated, and how the leader segments grow. The negative end actually grows in steps. We call this what's called a step leader. You may hear that a lot when we're talking about lightning.
Mm-hmm.
The negative end grows in these 50-meter steps. And it actually, you have the tip of the negative leader, you'll get a new segment grow, and a bipolar segment will grow with a positive end coming back towards the established negative end of the leader and a negative end going forward. And it connects and suddenly produces a new 50-meter segment, and it's a bright attachment. And so that's the step. The positive end, because electrons are coming in towards the tip of the positive leader, there's a deficit of electrons and they're being driven this way. They tend to flow more smoothly. And so they tend to just kind of move in a continuous fashion without the stepping. There is some stepping that we've observed, but it's much different. And there's just these behavior differences between negative and the positive ends that to me are incredibly fascinating. And the whole behavior on the positive end is what causes the multiple strokes that we see on the ground. And most lightning ground flashes are negative. In other words, a negative end of the leader connects with the ground. But after that process occurs, you're left with a growing positive leader. And the positive leader does these things where branches will decay, they reionize and form what we call recoil leaders. These come back down the channel as a dart leader and cause multiple strokes. But only the positive end behaves that way. The negative end does its thing, but it's much different. And it's very fascinating. And we're still trying to understand that.
That difference between positive and negative is such a wide dynamic. And on airplanes, we notice it a lot in that when you have bidirectional leaders coming off airplanes, the positive end starts first, and you actually have a positive leader moving probably hundreds of meters, and then a negative one will come off the other end of the airplane somehow. So there's just a totally different set of physics there. And on an airplane, it doesn't matter all that much. On things that are on the ground, it sort of does matter if it's positive or negative in a sense, particularly like wind turbines, because in a wind turbine, we don't have a lot of real estate that's actually conductive. There's just maybe the tip, maybe there are a couple receptors on the blade that are made out of metal. And whether the blade is positive or negative has a big influence on its protection effectiveness. And I think people have a hard time grasping that. Like if the cloud's positive, the wind turbine's negative, it means something different than if the cloud is negative and the blade is positive. It changes just the physics of the whole setup change. And because we don't know a lot about why, we can see it. If we're in the laboratory, we can see it, not like you can out in the wild. But we see the differences, but we because we're in a controlled environment. A lot of times when we're actually looking at sort of application of lightning to products, we don't see the full effect. Everything's too close. We can't generate the voltage of a cloud.
Right.
We can't generate the energy of a cloud and the voltage of a cloud simultaneously. So we try to work our way engineering-wise through that. But in the differences in positive and negative, how much difference in the physics does it really make? Like, is it just negative sort of steps along and positive travels much more evenly? Are there other differences between positive and negative that we are really learning about now from mostly photographs?
There is in what we see with upward lightning. And upward lightning is essentially a leader that initiates from an elevated object, building, a tower, wind turbine. There's an enhancement of the electric field locally due to the shape of the object. And so upward lightning, instead of being a bidirectional process, it's a unipolar in that it's a one polarity that initiates from this object and goes upward. And this can happen from tall objects in two ways. You can have lightning triggered upward lightning. And what that means is that there's a normal downward flash nearby, and that changes the electric field over this tall object and causes the initiation of an upward leader. So that's lightning triggered upward lightning. Or you can have just that object initiate something on its own without any other preceding lightning, and that's called self-initiated. And we see that more in the wintertime when the cloud bases are lower and the charge is much closer to the tower. We'll see that self-initiated. And it also relates to the wind speeds as well. What polarity do we usually see? Well, it's positive upward leaders. In other words, a positive leader develops from wind turbines and tall objects much more often than a negative leader. And I've only witnessed a couple of upward negative leaders in all my research. It's always been upward positive leaders. And that has to do with the charge arrangement over the objects at the time of the flash. And the most prolific producer of upward lightning from tall objects are what we call mesoscale convective systems. And so these are very well-developed storms. These take hours to develop into the scale that we're talking about. And you get this large convected leading edge, and then you get a less convective, but still with a lot of rain, a lot of charge that falls behind it. And we call that the trailing stratiform precipitation area. But what happens is that, even though charge is being generated in the updraft and the leading edge, that charge gets ejected out and becomes a very strong layer of charge. So there's a big table of charge over these tall objects. And then you'll get a flash. Most times it occurs in the convected leading edge, but the leaders always go to where the charge is. They're attracted to that charge.
Sure.
So they will follow these long pathways over this horizontally stratified charge and propagate over these tall objects. And it's these typically it's negative leaders that go over a large horizontally stratified positive charge region. So we get this positive charge region in the trailing stratiform over these tall objects. You get negative leaders that propagate over that, and that causes a very fast, intense electric field change. And due to the enhancement of the shape of the object, it causes an upward positive leader to rise up in response. And we've seen up to 14 wind turbines. I've seen, of those 10 towers, I've seen 9 of them light up at one time in Rapid City.
Wow.
And they all rise up in response to this negative leader that's going across. So that's the triggering mechanism is the field change due to the triggering component, which is the negative leader. So as far as the positive versus negative, we usually see positive leaders rise up from tall objects, wind turbines and such. And that has implications because, like I mentioned before, positive leaders behave in a way to where they will branch and they decay, and then they reionize on these decayed branches, which we call recoil leaders. And again, this is a bidirectional bipolar process.
Right.
And the negative end comes back down and follows the path to ground back to the where it initiated, the turbine blade or the point of the building.
Right.
And it'll do it multiple times. So it keeps getting these pulsing events that strike that object multiple times. And because it branches out in many directions and there's such an area of charge, a large area of charge, these flashes tend to last longer. They generate more current spikes to the object and more heating.
Yeah.
So it's kind of like the worst case scenario. You really don't want to have that scenario where you can sustain it for so long and have multiple pulses like that, but that's the case. So that's a clear example of how the positive and negative difference makes a difference in wind turbines and other objects. Downward flashes, you can have negative or positive, where either a negative leader comes down to a positive leader. Normally it's the negative end, but sometimes there can be a positive end. And in this trailing stratiform precipitation area, there's a lot of positive flashes. The positive cloud to ground flash is the lead triggering flash for upward lightning, because a positive end comes to the ground, the negative end is propagating through that negative charge region. There's a return stroke. And then there's a rapid development spread out of the negative leaders that causes the upward positive leaders. So positive CGs are the triggers, the most efficient triggers for upward lightning. When downward, and they tend to also be very high current, high peak current, and long continuing current.
Sure.
If you get a downward attachment to a tall object wind turbine, the energies are much higher. And so you can get more damage with just in a downward attachment with a positive CG. So positive CG downward flashes can wreak havoc more so than a negative.
And that has implications from the scientific side of, we're really just learning about some of these lightning strikes and how powerful they are. I know there's certain places in the world like Japan, off the coast of Scotland, Croatia, and Turkey, and some parts of Turkey. The lightning strikes are just sometimes massively strong things. And you photographed some of those or created videos, slow motion videos of some of these attachments in South Dakota. So there were some really interesting ones you published over the last summer. And it speaks to what you were describing, where there's lightning reaching up from multiple wind turbines out to the sky. And then you'll have an attachment to one of them. One of them will take the attachment. And you'll just see multiple flashes occur as this wind turbine is spinning. And such that the lightning actually follows the wind turbine blade through 30, 40, maybe 50 degrees of arc rotation. That's a lot. And hot blades. So it'll jump from one blade to another because, like you were saying, the lightning tends to want to pulse there. So it'll flash on, flash off. And in that off period, it just kind of hanging around waiting for more energy to feed it. And maybe it jumps to the next blade, maybe it doesn't. But those are things that maybe 10 years ago we thought didn't exist all that much. And now with some of the images you're providing and others, it's really making everybody, at least our company, go back and look and say, okay, what's really happening here? And as we continue to use sort of 1920 to 1930s data sets for lightning, that's not what's happening in South Dakota. The Switzerland Tower, Italy Tower, all the things that were done early on, which are the foundation of all lightning protection today, those are true. Those are all still true. They're all still valid. But there's other effects that are happening now. And so when you go out to video, high-speed video wind turbines, what are you expecting to see there? And how do you know, like, tonight's the night, I need to get out there tonight because this is the storm? Is there some part of that, like, you can tell by the structure of the storm, this one's going to be a big one?
We can. I mean, it's gotten to the point now where I can actually tell you when we're in a zone that's favorable for upward lightning during a storm. And
wow.
we, 80% of the time, that's what happens, or that's when it happens. So, like with anything, the more you watch it, the more you learn about it, the better you can understand it. And that's, I've been doing this, for many years. And, my colleagues and I can sit there and tell you the polarity and, the behavior in real time. And that knowledge has come through the high-speed analysis. But now it's to the point where I can tell you just by looking at a flash in real time, whether it's negative, it's positive. And it's amazing. It slowed it down for us in our minds as we watch it. So I'm looking for these mesoscale convective systems to form with a trailing stratiform precipitation area. When I see those, I go to any object that's tall and pointy and try to film. Rapid City has some towers. There's some other big towers in western South Dakota. We now have this wind turbine farm. This was the first year that was operational, so this is why I got the footage. So first chance that I saw a storm that had the favorable characteristics and was likely to produce it, I went out there and sure enough, it produced upward lightning. So I knew it was favorable. Yeah. So I'm watching the storm dynamics. I also have the background to forecast using the models and have an understanding of when storms will be favorable or conditions will be favorable. And then I can see the radar development and actually tell you, this is doing what it needs to do to produce this type. Not all the time it happens. There's some aspects that I'm still not clear on. Is like, this was a perfect scenario. Why didn't it happen? And it has to do with charge levels and such that are just not optimum at that time. So I'm trying. I can forecast when the conditions are favorable. I can tell that a storm is likely to produce it. And then when I go out to actually film it, it all depends on what I'm trying to observe. Sometimes I want a more wide field view and I want to watch the triggering process where the leaders move over and cause the upward. So, I need a bigger picture on that. Sometimes I want to see more about the attachment and zoom in on the tower tip and see what's going on. If there's attempted leaders prior to the initiation of a streamer to leader transition. So it all depends on what I'm doing. And that also dictates the speed at which I'm operating the cameras. These very fast processes, I have to be up in the 50,000 images per second range. For the more big picture triggering process, 10,000 works for that. So it all depends on what I'm trying to look for. But, this was the first year that I actually captured wind turbines where I saw that arc. And essentially you have this blade that's moving this way. It initiates an upward leader. It's moving this way. And so there's a luminous arc that's being left behind. And then it cuts off. And then the upward moving blade, same channel. And then this portion decayed. The whole thing decayed. But then a dart leader came down and it connected here rather than going that path. So it's just a matter of the decay, the cooling of the channel, and what's most favorable electrically. Right. The electric field was enhanced and more favorable to attach when it came back down than it was to go over here. And this had decayed enough so that it was less conductive.
And that's the physics of that are really interesting because you're not just looking at a sort of a stationary plasma channel that is still getting blown by the wind. It's more like being in an airplane. And the way I see it is being in an airplane. Like when you see a wingtip get struck, you feel like you're dragging the lightning behind you. It's following you. It has to follow you because you're the conductive path to where it needs to go. And it's going to follow that. It's going to follow that pathway until it no longer can. And if it can't follow that pathway, it's going to find a new pathway to go to. And that's the blade hopping aspect of it, which is a completely set of different physics because they're not only looking at the plasma of the channel and all the positive and negative pieces of that and dart leaders on top of it. Now you're looking at you're in a windy environment. The blades are moving at relatively high speeds, 200-ish miles an hour, somewhere around the tips. So it becomes this really complicated physics problem that and you have the cooling of the channel, the plasma channel is changing and it's growing, decreasing all the whole time. It's like this living, breathing dragon out there. It changes everything. And I think what your videos are doing for the world right now is just giving us another perspective on it. Obviously, we can do a lot of things computationally with lightning, right? But what you're seeing is some of that live action. Hey, this is what's really happening. data set, which we haven't really had a good feedback loop here outside of what happens in the laboratory. And we've been very successful in the laboratory. We're not as successful in the real world. And your data is providing us the why, and maybe not how, right yet. Maybe not the how, but the why. Like, oh yeah, this is a lot different than what we planned for. Oh, okay. Now we need to rethink about what's happening.
And do we need to design lightning protection differently, knowing that it's going to attach maybe multiple times, and it's spinning and it's moving? I mean, what are the implications? Yeah,
and on an airplane, I think one of the interesting pieces on airplanes is, as Tom was alluding to earlier, when he got struck in the airplane and it hit the prop and then it went over his canopy. That same thing happens on commercial airplanes, right? So it starts at the nose and the lightning travels along the fuselage. There's a lot of aerodynamics that happen in the middle of all that, of where lightning will attach to, and if it runs into things, and gets the airflow shoves it around, and we've just sort of haphazardly say, well, it doesn't really matter, right? It doesn't make any difference, but it does, and particularly with wind and the correlation with wind turbines, airplanes are almost all conductive. There's not very few parts of an airplane that's not conductive. On a wind turbine, there's very few parts that are conductive. It's the opposite of an airplane. So what we've been taking for granted on airplanes for 100 years almost is now all of a sudden super important to us because we're trying to control where lightning goes, right? The goal of a wind turbine is to manipulate the physics such that lightning only goes where we tell it to go. But lightning doesn't want to behave that way. And it doesn't want to do what you tell it to do. And part of that is a combination of the positive, negative aspects of it, the dart leader part of this, and what actually is happening up in the cloud. as charge centers get reached or breached, it's changing what's happening down at the bottom down here, which is us. And that's where I think our sort of our fundamental understanding and what we think we can do control-wise on lightning needs to be reevaluated.
Absolutely. I mean, I think to your point about the high-speed video, what it's done for us is allow us to see lightning like never before, and we were able to see it in a way that the human mind can understand it sequentially in a video, as opposed to these streak cameras that were very hard to interpret, but they were useful in analysis. And we can explain it in a way that we can understand and the general public can understand. So I think, to your point about the high-speed cameras, they've really furthered our understanding of lightning and our explanation of lightning, because you can see it. You can see that this is the process. I alluded to the bipolar development of a lightning flash. We have video of the actual leader starting in clear air, and it was near another channel that formed, and essentially it forms and you see the positive end bright, non-branched, you see the negative end highly branched, stepping like I explained, and you see it grow bidirectionally, and then the negative end actually attaches to the positive leader and forms a new branch. And to me, this is the most incredible observation, because we're actually seeing that leader form, and that bipolar, bidirectional process is confirmed, and we can see it, and it's very clear. And that was something that was proposed in the 60s and challenged very heavily for many, many years.
Oh, yeah.
It was 20 years before that idea was proven to be true. And now we can see it easily with the cameras. So, there's a lot of aspects, and, if we evolve our thinking and understanding through the use of these cameras, and you have to, I will say, it can only, you only further your understanding when you combine these optical observations with electric field measurements and lightning mapping array and all the other observation techniques you use. You really need to use all these in combination, because we can't see in the cloud, but we can map the lightning in the cloud and draw a picture of what's going on while we're seeing the optical portion. So it's important that there's a lot of data collected in many different ways that allow us to improve our understanding. So.
And Tom, I think the common conception, at least this was mine, is that, the Earth just has X amount of lightning strikes. Obviously, there's storms everywhere around the world, and when when everything is right, then they happen. But, these wind turbines are actually causing more lightning than would otherwise be there if they weren't erected on that mountaintop or in that field in the Midwest or out there on offshore. Is that's true, that because they're there, they're causing more lightning strikes, even more so than maybe a stationary building? It's
definitely true that we're seeing more lightning created by objects that are man-made. If those wind turbines were not there, if those tall buildings were not there, when you have a triggering flash nearby, there would not be upward lightning, because there's not the object that enhances the electric field. So you're still going to get the naturally occurring lightning, the downward lightning, but we're seeing additional lightning generated due to the addition of tall objects, wind turbines, and tall buildings. I don't know if there's a difference in the percentage or the numbers between wind turbines versus tall objects, because you can get very tall towers that enhance the field greatly. And so they can produce a lot of upward lightning. Wind turbines tend not to be as tall as some of these, 1,000-foot towers that you see for communication towers. And those things light up. I mean, there was one, the Toronto CN building in Toronto produced 35 upward flashes in one storm in three hours. So, I mean, the numbers, and I saw the same thing in Norman, Oklahoma. There's a tower farm north of there, and I went down there and I filmed over 30 flashes in one night. So when you get those really tall towers, those things are prolific. The wind turbines being shorter, but the blade is moving, that enhances their effective height, if you will. And you have more of them. So you can get, that's where I filmed these multiple things where you can see, 10 wind turbines in one shot. So it's difficult to quantify, if one is more effective than the other in producing upward lightning. But we know that more lightning is being produced, the more taller buildings that we create. And you can actually see this too in the lightning climate data or climatology data or history data. If you look, in fact, one of the tools that we use to determine if a tower is producing upward lightning is we'll look at the density plots, and you'll see this peak of activity right where the tower is. And that tells you that there's much more lightning occurring there. And it's all these multiple strokes from the upward lightning flashes that's increasing the density of flashes. It's not because it attracts downward lightning more prevalently, because that's a natural process, and that density is going to be uniform over the area. But if you see an enhancement right at the tower, that means it's producing upward lightning because you're getting more of these attachments.
Well, Tom, as we wrap up here, I have two questions for you that I think everyone wants to know. One, can you send us back in time? And two, do you own a DeLorean?
I'm afraid the answer is no to both of them. Sorry about that.
Disappointing. And on a more serious note, where can people follow up with you on the web? I know you have a ton of videos, obviously, on YouTube, and you have your blog. Where can people learn more and see some of the stuff that we're talking about?
ztresearch.blog is my blog. So ztresearch is also my Twitter. Those are my two primary sources of reaching out into the community and sharing things. I do have a YouTube site that has both my lightning and my just regular photography, landscape, weather photography, my atmospheric wildlife, if you will. That is on YouTube, and there's links from my ZT Research blog that will get you there. So pretty much if you go to the ztresearch.blog, that'll get you everywhere you need to go. And then you can see me on Twitter.
And as always, we'll link to all that in the description below, whether you're on YouTube or Spotify, iTunes, Stitcher, wherever you're listening. Tom, thank you again so much for coming on the show. We really appreciate it.
Well, I really appreciate the opportunity to share this with you guys and discuss this. This is fascinating things. Wind turbines, I've always been fascinated since I was a little kid with wind turbines. And it's hard to believe that I'm actually studying them and the physics related to the lightning in association with them. So I really appreciate the opportunity.
All right. Well, again, we want to thank our guest, Tom Warner, for coming on the show with us today. Fantastic topic. And again, he's essentially the lightning researcher for lightning researchers. So we really appreciate his work for just the greater good of all of us, whether it's aircraft travel and, of course, keeping renewable energy like wind turbines, going. So again, follow up with Tom at his website, which we'll link to in the description of this podcast, which is ztresearch.blog. And be sure to send him a note and thank him for his time on the show and ask him any questions you might have. You can, again, reach him through that website. So thanks again for listening. Be sure to subscribe, share the show with a friend, and we'll see you here next week on the Uptime Wind Energy podcast. Operating a profitable wind farm is all about mitigating costs, minimizing risks, and being efficient with maintenance, repairs, and upgrades. It's incredibly expensive to send a team of rope access technicians up tower to make even simple repairs. We also know how costly lightning damage can be, requiring inspection, repairs, and downtime for even minor lightning strikes. This is why it just makes sense to install a WeatherGuard Strike Tape LPS upgrade the next time your technicians are going up tower. Maximize the time efficiency of your techs and prevent future lightning damage by installing our Strike Tape LPS upgrade the next time your crews are going up on ropes. Learn more in today's show notes or visit us on the web at weatherguardwind.com.